This video is a short introduction to integer programming and scheduling. So we start with the GNU MathProg language, and there's this is part of the GNU GLPK project, and you can find an online version at the following website. All right, so let's take a look at one of the examples, and that's the Jesuit Volunteer Corps. So there are 7 people in the house, broken down the chores into 4 major sections: kitchen, bathroom, common area, and trash. Trash is the only task that needs only one person to accomplish. The other 3 tasks have 2 people assigned to them. Each person needs to rotate through each task twice, and the trash only once. The assignments rotate each week. Each person needs to have a new partner each week, and no person can have more than one task in a week. So the way we're going to solve the problem is slightly different. We're going to require every possible pair to do at least one task together. All right, so how do you solve such a problem? So the idea is to use a modeling language, sort of like a mathematical programming language, a combination of a traditional programming language and a linear program. And when you put the two together, you can generate very large linear and integer, mixed integer programs very easily. All right, so we start the number of weeks to schedule. So there are 7 weeks to schedule. There are 7 volunteers, so we define a set of volunteers. These are our 7 people. We have 4 tasks to accomplish. So kitchen, bathroom, commons, and trash. And the weeks will go from 1 to T. We already said up above that T was 7. Okay, next we want to figure out all the possible pairs. So there's 7 choose 2 equals 21 possible pairs of people. And a nice way to get MathProg to iterate them is by defining the set of pairs as the set of ordered pair U comma V, such that, so this colon here means so that, or such that, U is less than V. And so this is your set of pairs. And this guarantees that we don't double count any pairs, and we don't pair anybody with themselves. Okay, so the key is variables of the form with triple subscripts VTW. So if volunteer V is assigned to task T in week W, then this binary variable is equal to 1. Otherwise, it's equal to 0. So in this line, line 17, we can define many variables for each volunteer times the number of tasks, that's 4, times the number of weeks, that's 7. So we define almost 200 binary variables in this one line here. Next, we need binary variables to make sure our pairs are assigned tasks. So if pair UV are assigned task T in week W, then that binary variable P is equal to 1. So this is a variable with 4 subscripts. All right, so we define it right here. UV is in pairs, T is one of the 4 tasks, W is in weeks, and it's a binary variable. All right, the objective for this problem is we want to minimize the number of times any given person has to take out the trash. All right, so here's our objective. Our objective is to minimize Z, but we're going to define Z below. Z is not tied to any constraints yet. All right, so we have a lot of constraints to encode. We'll go through some of them. So the first one is each volunteer must be assigned exactly one task. So what this command does here is it sets up 49 constraints for each V in a volunteer, for each W in weeks. We have 7 times 7, 49 constraints. And for each one of those possibilities, we want the sum over all 4 tasks to equal 1. In other words, exactly one of these variables is going to equal 1, and the rest must be 0 because they're all binary. They're only allowed to be 0 and 1. All right. Now for each week, so this is the next 7 constraints for each W in week, the sum over all the volunteers of their decision variable should equal 1. Assigning them to trash. In other words, volunteer V is assigned to trash in week W only one time. So each week, because week is what's fixed, week does not change. So for each week, only one of the volunteers will get trash equal to 1. So what this means is only one volunteer will be assigned trash per week, and exactly 1. And for the other tasks, we want 2. So for every task and for every week, except such that T is not equal to trash, so except for the trash. So for the 3 tasks that are remaining, and for the 7 weeks, so there's 21 constraints here. If you look at all the volunteers, exactly 2 of them will be assigned task T in week W. So T and W stay fixed. They do not change in this sum. V changes. So given a task, given a week, except trash, exactly 2 of the 7 volunteers will be assigned to that task in that week. All right, and we continue in this manner, getting more and more constraints. Each volunteer must cycle through each task twice, at least twice, so this constraint would do the trick there. And what is a little tricky is the objective. So this line 38, what this would guarantee is that the maximum value of the number of times any volunteer has to take out the trash, that maximum number is less than or equal to Z for every W, and for every volunteer. So for the first volunteer, let's say they take out the trash 2 times over all the weeks. So for 2 weeks, they have to do the trash. That will force Z to be at least 2. And then if another volunteer, say volunteer 3, has to take out the trash 3 times, this sum will equal 3. But this is the same value of Z. So what Z becomes is Z must be greater than or equal to the maximal number of times any given person has to take out the trash. Finally, we have to make sure that the pairing decision variable is consistent with the individual decision variable. So suppose that pair UV is assigned task T week W. Okay. Well, that implies that individual U has task T week W, and it implies that individual V. So if this is a 1, it forces the right-hand side to be a 1. If the left-hand side is a 1, it forces the right-hand side to be 1. So this implies both of these are 1. And conversely, if this is a 1 and this is a 1, 1 plus 1 is 2, take away 1 is 1, so that implies that the pair is assigned the task. In other words, if person U is assigned a task in a certain week and person V is assigned the same task in a certain week, then that would imply that the pair of the people UV is assigned a task. And every pair must do at least one task together. So greater than or equal to 1 means at least one of these variables must be 1. They're not all allowed to be 0. All right, so we now do some post-processing here. This basically just will print out a nice table. So let's go to the actual computer where we downloaded the file. We just cut and pasted it. I called it small Jesuit mod. So here's the same file again. I'm using a neat program called Text Wrangler, and let's open a terminal window. This is an Apple computer. It's basically a Unix shell that we can open, and let's run the program. And at the same time, I'm going to generate an LP file, which is the IBM Cplex format. So let's run it. And it takes about 50 seconds, though for some reason it runs on the website JavaScript version in about a second. I'm not exactly sure why that occurs, but you can run it right here. And you'll see it runs it in JavaScript version of the solver. And if we look at the output, here's the output. So this is the log file. And perhaps it's solving with a different option, but it's solved. One person is the objective, so the objective is 1, which means one person has to take out the trash. Each person takes out the trash at most one time. And if we look at the output from the computer, it's still running. It's going for about 60 seconds and it just solved. So let's see some of this output. This is the GLPK solver. It's called GLP Sol solution, and it's part of the GLPK project. So we ran the program, and it took 74 seconds to solve on a pretty fast computer. It used 6 megabytes of RAM. And here's the schedules. So week 1, volunteer 1 does the commons, volunteer 2 bathroom, volunteer 3 bathroom, volunteer 4 kitchen, volunteer 5 trash, 6 commons, and 7 kitchen. Notice they're paired up except for the trash. So to show you very quickly what this LP file looks like, let me open it up. So here's the small Jesuit LP file. So this is the file. It's 4,000 lines, and these are what some of these constraints look like. So the first constraint, to make sure that each person was assigned volunteer 1 was assigned in the first week exactly 1 task. You see the sum of the 4 variables is equal to 1, which means exactly one of these must equal 1. So if you look more carefully, there's probably hundreds of constraints here. All right. So I wrote a bigger version of the problem to make it a little more challenging. And just to show you how fast things solve and how things scale up, let me show you how fast it solves on some of the other programs. So another program is called CBC Coin. It's the CBC Coin OR project. And let's solve the same problem. Notice it solves in 99 CPU seconds. Wall clock is how much actual time it took. So 1.11 second. Another program is called SCIP. So CBC was free. Another program that's free is called SCIP for non-commercial use. And look how fast that solves. Looks like it solved even faster. Total time, 0.35 seconds. All right. And there's a very expensive commercial solver called Gurobi. And that solved the problem in 0.88 seconds. But let's make the problem a little harder. So far, we have about 50 seconds for GLPK, and the other two solvers solved it very fast. All right, so the other version is, let's make there be 9 weeks and 9 volunteers. And I added one more task library. So it seems like it's only a little bit more, right? So it turns out that if we go back, it literally took forever for GLPK to try to solve this. I cut it off at 6,000 seconds. So almost 2 hours, a little less than 2 hours it ran. It knew the best solution was greater than or equal to 1, but it was not able to find an integer solution. All right, so remember, so the free version, GLPK, 6,000 seconds. CBC, when you try to solve it with CBC, it definitely does better. It does solve it eventually, but I believe that it takes about 300 seconds. So all right, so CBC does solve it, but I believe what it takes is about 300 seconds. But it's having trouble. It's not solving it very quickly. Try SCIP. So it's looking for a solution. It knows from the relaxed LP that the answer is at least 1, but it hasn't yet found a integer solution. It has an infinite gap still. So this will go on for quite a while, and it'll also take about 300 seconds or so. And notice this is only a very slight increase of the original problem, and you see how quickly it becomes hard to solve. However, it looks like we would not be able to use this for a real problem. However, let's try Gurobi. So we try Gurobi. It's going to use 4 threads to solve it at the same time. Some of the solvers have the capability, and notice it solves it in 12.37 seconds. Okay, so that is extremely fast. If we want to specify to use 8 threads, this is an i7 CPU. I usually do 7 because I can leave half a CPU to do other stuff, but if we do with 8 threads, you could see right here how it's using all the full CPU, solves it in 9.93 seconds. And you can experiment. Sometimes more threads is not better. 6 threads. All right. So going back to CBC, let's set the threads to 8, and let's I think import Jesuit.lp. Let's solve. So this is probably the best free program out there. Though it's the best free program out there, it's light years behind Gurobi and Cplex. So what it's doing now is it's doing some heuristics, some pre-processing, and in a minute it's going to start to go through the tree and try to eliminate non-integer solutions. Very quickly it finds the linear program solution, the relaxed solution, and the whole main job is to go from the solution of non-integers, which is easy to find, to the solution consisting of integers. That's the hard part. So if you just solve it and don't tell the solver that these are integers, it'll give you answers that are all fractions that don't make any sense, like a person could be assigned 1/3 and 2/3 to doing the trash. So it doesn't make physical sense, but it makes sense mathematically. That's called the relaxed LP. And thanks to the Cplex method, that solves very quickly. So the best possible solution, that's 1. That's the solution to the linear program, relaxing all the integer constraints. And notice right now, it thinks the best solution is absurdly large, pretty much infinity. So it has no idea what the integer solution is. All right, so this will go for a little while. Another option is Cplex. So it turns out that Cplex and Gurobi share a common heritage. The people who started, the person who started Cplex, I believe it was, I don't want to say, I don't know for sure, but the people who started Cplex were bought out by IBM, and then at some point they left IBM and started Gurobi. All right, so back to CBC. It solved the problem, and using all 8 CPUs, it solved it in 156 seconds, which I think is about twice as fast as it would just using a single CPU. And it used 871 CPU seconds. So as you can see, this 156 is much, much worse than Gurobi at 15 seconds. And when the problem gets even more complicated, it just becomes unsolvable with the free programs. All right, so this concludes the introduction to integer programming and scheduling. Take a look at the excellent website www.nd.edu/Jeff\MathProg for many other interesting examples of integer programs. And the moral here is, if you really need to solve if you have a program and it seems to be taking forever, it might just be your solver. There's a world of difference. There's a magnitude of difference between the free solvers, several magnitudes of difference between the free solvers and the commercial solvers.